Alrighty, in this video we are going to be talking about growth and decay. In many applications, the rate of change of a variable y is proportional to the value of y. If y is a function of time t, the proportion can be written as dy dt is equal to ky for some constant x. This initially said dy dx. Either way, it's going to be the same thing depending on what your thing is, whether it's x or t. In this case, we're going to be using time t just because in these applications, we're going to be working a lot with time. Number one just says, prove that the exponential growth and decay model is y is equal to c e to the kt using separation of variables. So we're using the same thing that we've been doing in terms of what we did before break in Unit 6a, where we're using separations of variable. So I'm going to divide y, multiply x, not xt, so that I have 1 over y dy is equal to k dt. I am going to integrate both sides now. So that's going to leave me with ln of y is equal to kt plus c. I am going to solve for y now, so that's going to be me taking the e of both sides. That's going to be y is equal to e to the kt plus c. And remember that using my properties of exponents, I can split this up into two parts now so that I can have e to the kt times e to c. Using my properties of exponents, remember that if I add, I can split this up into two multiplication terms. So I have e to the kt times e to the c. And we know that e to the c is some number. What number that is, I don't know, and I don't care. So that's why we can replace that with c. And that's how we get my formula of y is equal to c e to the kt. All right. We are going to be using that formula to work with some of these forms right here. So number 2 says the rate of change of y is proportional to y. When t is equal to 0, y is equal to 2, and when t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? This essentially is going to be like a systems of equations problem, where you need to figure out what your k value is before you do anything else. So remember that my model is going to be y is equal to c e to the kt. Now for the first one, it tells us that t is equal to 0 and y is equal to 2. So I have 2 is equal to c, e, and then k times 0. Well, k times 0 is just going to be 0. So then I have 2 is equal to c e to the 0. And remember that e to the 0 is just 1. So this tells me that my c value is going to be 2. So that's my first step, finding out what my c value is. All right. After I get my first step, my second step is to find out what my k value is. So I already know that c is 2. And I want to find out what k is based off of my second thing that I know. I know that when t is 2, y is 4. So once again, I have 4, e, 2e, and then t is 2, so 2k. I need to figure out what my k value is now. So now I'm going to solve for k by isolating k. So I'm going to divide by 2. Then I'm going to take the ln of both sides. And then I'm going to divide by 2 again. So this means that my k value is ln of 2 over 2. And my third step is to figure out my final equation. So now I know that c is 2. And I also know that my k value is ln of 2 over 2 times t. And it tells us what is the value of y when t is equal to 3. So that's just me plugging in 3 for t. And I get that. Just leave it like that and call it a day. So 2e to the ln of 2 over 2 times 3. All right, number 3. This is where we start having the applications coming in now. We have a rate at which a population of fruit flies grows is assumed to be proportional to the number present. And we have 100 fruit flies initially, and after 3 days, there are 200. We don't want to find an expression for the number of fruit flies in the population at time t is greater than or equal to 0. And then we want to figure out when will there be 1,000 fruit flies in the population. So part A is essentially this 3-step process here where we are going to find the equation. So the first step is to find out what C is, and that's always going to be using my initial value. So it tells us that we have 100 fruit flies initially. So we know that if I were to plug in 100 and T is 0, that means that C is going to be, plot twist, 100. My second step is to find out what my K value is, knowing that I have 100 now, and it telling me that after 3 days, there are 200 fruit flies. 200 is equal to 100 e to the 3k, and I'm going to solve for k. Divide 100, so that's going to give me 2 e to the 3k. I'm going to take the ln of both sides, so now I have ln of 2 is equal to 3k. Divide by 3, and I have ln of 2 divided by 3, and that's k. Which means that for part A, my equation is going to be y is equal to 100 e to the ln 2 over 3 times t. Part B, well, this is A. Part B tells us when will there be 1,000 fruit flies. So when y is 1,000, what is t? Okay, so I'm going to divide by 100, and that's going to give me 10. So now I have 10 is equal to e to the ln of 2 over 3 times t. And I'm going to solve for t. So I'm going to take the ln of both sides. Taking the ln of both sides, I'm going to get ln of 10 is equal to ln of 2 over 3 times t. And then to solve for t, I'm just going to take the reciprocal of this and multiply that out. So that means that t is equal to 3 ln of 10 over ln of 2. What is that? I don't know. This is probably going to be in the calculator inactive problem anyways, so I don't care. If it was a calculator active problem, just, plug it in, see what it is. Of course, round it to the nearest thousandths, okay? Don't give me 2 decimal places by now. Hopefully you're trained by now to give me 3 decimal places. All right, number 4. After a person drinks a cup of coffee, the amount of caffeine in the person's bloodstream is 30 ppm. Suppose that the amount of caffeine decreases at a rate proportional to the amount remaining, and after 4 hours, there are 14 ppm left in the bloodstream. How many hours will pass until there are 10 ppm left in the bloodstream? All right, once again, I'm going to have to find out what C is, and then I'm going to find out what K is. Okay, so my first step, we already know what my lovely formula is. Y is equal to C e to the kt. And it tells us that at time 0, there's 30 ppm. So we know that, hopefully, that C is 30. So 30, C e to the 0, plot twist it is, great. All right, step 2. We know that C is 30. Now we need to know what K is. In order to figure out what K is, it tells us that after 4 hours, there's 14 ppm left. So that means 14 is equal to 30 e to the 4k. This is going to get pretty messy because I'm going to have to solve for k. And in this case, I'm going to divide by 30. That's going to give me e to the 4k. And then I'm going to take the ln of both sides. And then divide by 4. That's going to give me k. Okay, my third step is going to be my equation. So that's going to be 30 e to the ln of 14 over 30 over 4 times t. I know, it looks messy. Bear with me. That's your formula. Now, step 4 is going to be you plugging in 10 now. So you have 10 is equal to 30 e to the ln 14 over 30 over 4 times t. And then, of course, you're just going to solve for t. 10 over 30 is 1/3. E to the ln of 14 over 30 over 4 times t. Take the ln to both sides. And then to solve for t, you're going to take the reciprocal. And that's going to give me 4 ln of 1/3 over ln of 14 over 30. What is that? I don't know. But guess what? Just keep it like that. Okay? The AP graders will be happy if you keep it like that. All right. Let's see. I guess I could do 5. 5's fine. Okay, we have bacteria in a certain culture increases at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, how many hours will the number of bacteria triple? Okay, so you have y is equal to c e to the kt. Now, here's the thing. We don't know anything about my initial rate, aka what my C value is. And honestly, I don't care, because the thing is, it tells us that the number of bacteria doubles in 3 hours. So what I'm going to do is double my bacteria. In this case, I'm going to have 2C. Remember that C is going to be my initial population, so I don't know what that is. But I do know that C times 2 is double that. And then I'm going to have CE to the 3K. I'm going to solve for K. That's going to give me 2 e to the 3K. ln of 2 is equal to 3K. K is equal to ln of 2 over 3. All right. Now, it tells us that how many hours will the number of bacteria triple. So now, instead of 2C, we're going to have 3C. But I already know what K is. So now I have 3C is equal to C e to the ln of 2 over 3 times T. So we have 3 is equal to e to the ln of 2 over 3 times T. Then I'm solving for T. By now, you should get the hang of this. This is just repetition of what you're doing. And your answer is 3 ln of 3 over ln of 2. All right, number 6. Population over y grows according to the equation dy dt is equal to ky. We already know that formula. K is a constant, t is measured in years. If the population doubles every 10 years, then what's the value of k? Notice how we don't know what c is, because remember, it is doubling every 10 years. So, remember that I have my original equation, y is equal to c e to the kt. And if it's doubling every 10 years, I have 2c is equal to c e to the 10k. I'm solving for k. So 2 is equal to e to the 10k. Take the ln of both sides. So that means that k is ln of 2 over 10. All right, number 7, we have radium-226 loses its mass at a rate that is directly proportional to its masses. The half-life is 1,590 years, and we start with a sample of radium-226 with a mass of 100 milligrams. All right, so we want to find a formula for the mass that remains after T years. Now, if you took chemistry, then you should know the half-life formula. We also talked about the half-life formula back in pre-calc. However, in this example, we are actually going to derive that formula using, of course, separation of variables. Or in this case, we already know that the formula is y is equal to c e to the kt. All right, now we already know that we start off with 100 milligrams. And remember that C is, of course, my initial population. So now I have y is equal to 100 e to the kt. And it tells us that the half-life is 1590 years, 1,590 years. So instead of 100 now, we have 50. And based off of that, we know that my time is 1,590. So we have K and then 1,590. We're going to figure out what K is. And plot twist, we'll see that it's going to be very similar to the half-life formula. 50 over 100 is 1/2. So we have 1/2 e to the 1590K. And then since we're solving for K, I'm going to take the ln of both sides. So ln of 1/2 is equal to 1590K. ln of 1/2 is equal to ln of 1/2 over 1590 is equal to K. So your formula is 100 e to the ln 1/2 over 1590 times t. Now you might be thinking, that doesn't look like the half-life formula. Well, I haven't done this in these past couple examples right here, but remember how E and ln are besties and they are inverses of each other. So what we're going to do, remember, is E times the ln of whatever that number is, in this case 1/2, I'm going to have 1/2 as my base now. I still have time t, and of course I still have 1590 in terms of my denominator, and look at what we have, the half-life formula. Isn't that crazy? I know. We're talking about doing calculus with chemistry. That's crazy. Wow. All right. Part B just says find the mass after 1,000 years. This is just a simple plug and chug problem where you're just plugging in 1,000 into t and then calling it a day. This is probably a calculator active problem where you're just going to have to figure out what that is. What is it? I don't know, but use your 84 to figure that out. Part C says when will the mass be reduced to 30 milligrams? So that's going to be your y. So 30 is equal to 100, 1/2 t to the 1590. And then, of course, we are just going to, once again, solve this. So you have 3/10 is equal to 1/2 t over 1590. And then, of course, we are going to solve for t. In order to solve for t, since this is in the exponent, we are going to log it. So I have log 1/2 of 3/10 is equal to t over 1590. And then solve for t, I have 1590 times log 1/2 3/10 is equal to t. Now, this answer might look a little bit different than what we've been doing, such as, let's say, number 5 right here, or number 4, or number 3. However, remember that we can use the change of base formula to make it look like that, just in case you do want to do it. So that's going to give us 1590 ln of 3/10 over ln of 1/2. Of course, you could verify that that is equivalent to this right here, and this looks like these formulas right here. Of course, for these types of problems right here, like 3 and 4, you don't have to keep your equation like this right here. Remember that since you know that E and ln are besties and they're inverses of each other, this can also be rewritten as 100 2 to the t over 3. That's an equivalent way to say 100e to the ln of 2 over 3 times t. The reason why I kept it like that is because for you to see how we are getting c and how we are getting k in terms of y is equal to c e to the kt. All right, in the next video, we will talk about Newton's law of cooling and work on these two examples.